Good afternoon, friends. Welcome to the lecture of real analysis. Till now, we have seen some basic notions which are useful to understand the paper of real analysis. From today's lecture, we will start the actual syllabus. As I told you earlier, there are 4 units in the paper of real analysis 1. The first unit is Riemann integration, second unit is Riemann-Stieltjes integration, third unit is multivariable differential calculus, that of fourth unit is implicit function and extremum problems. In today's lecture, we are going to start the first unit of Riemann integration. Let me present my screen to you. Is the screen clearly visible?
Yes, ma'am.
Yes, ma'am.
Actually, if you look at this heading, chapter number 1 is Riemann integration. Okay, let us try to understand the meaning of both the words first. Okay, we are familiar with the word integration because we have studied integration right from our 12th standard. We have solved many examples also. Riemann is a German mathematician, Bernhard Riemann. Okay, let me just share my screen to show his photo. Okay, is the screen visible?
Yes, ma'am.
He was a mathematician, Bernhard Riemann. He was a German mathematician. Okay, he born on 17 December 1826 and died on 20 July 1866 at the age of 39. He was famous for real analysis, contributions in real analysis such as Riemann integration, Fourier series. Many contributions he has given in complex analysis, right? And also Riemannian geometry. Then he was known for many research in the field of real analysis. His PhD guide, that is doctoral advisor, is Mr. Carl Friedrich Gauss. We are having some theorems from Gauss also, right? No? Okay. Let us just look at some brief life history because it is always inspiring for us to know about the life history of the mathematicians. Correct. In the early years, Riemann was born, as we have noted, Riemann was born on 17 December 1826 in Briselens, a village near Danburg in the Kingdom of Hanover. His father, Frederick Riemann, was a poor pastor in Briselens who was found in the Napoleon Wars. Okay, his mother died before her children had reached adulthood. Then he has taken his middle school education in Lyceum. After his death of grandmother 1842, he attended the high school at Johnnium Lüneburg. Correct. Initially, his father wanted him to study a paper of theology or a subject of theology, but he is actually interested in the field of mathematics. Therefore, he started studying mathematics under Carl Friedrich Gauss. Okay. Then, with the due permission of his father, Riemann transferred to University of Berlin in 1847 to study the mathematics. Okay. Therefore, this was a photo Bernhard Riemann. Okay. Let us come to this. Let us come to my lecture now. Therefore, whatever is this word we have seen, Riemann was a famous German mathematician, Bernhard Riemann. What about integration? Integration we are familiar actually. No? What is the geometrical aspect of integration? This is giving us, what it is giving us geometrically?
Area or volume of curve.
Yes, it is area. In double integration, we are going for volume. For integration, we will call area only. Okay. Therefore, integration is mainly introduced in order to find out the areas of the plane regions. Okay. Actually, when we have introduced with integration, it was introduced as the inverse of differentiation. Correct? It was inverse of the differentiation. But historically speaking, the subject arose in connection with the evaluation of areas of plane regions, thus amounted to finding out the limit of sum. amounted of founding the limit of sum when the number of terms are tending to infinity. A realization that the subject could be looked upon the inverse of differentiation came afterwards. The reference to integration from the summation point of view was always associated with the geometrical concepts. To formulate an independent theory of integration, the German mathematician Riemann gave a purely arithmetic treatment to this subject, which is entirely free from the intuitive independence of the geometrical concepts. Many refinements and generalizations of the subject followed. The most noteworthy generalization was Lebesgue integration, which you are going to study in your second semester. Okay, what I want to say in simple words is integration is the word found out. Integration is the word introduced in order to find out the areas of plane regions. Areas of plane regions. I don't know whether you are knowing this or not. Therefore, integration is defined as the limit of sum. Integration is defined as limit of sum. Now we will try to understand why the definition was given as limit of sum. Okay, as discussed, it was used to find out the areas of the plane regions. Suppose I am giving you a task to find out the area of this region which is not having any specific shape. Okay, this area, whatever I have drawn on this monitor, this is not having any specific geometrical shape. Then a question arises, how to find out the area of this plane region. Okay, what one is going to do? What one is going to do? So, or suppose this is the plot I want to sell. This is the plot I want to sell and someone want to buy this. But in order to buy this plot, we should know the exact area so that the buyer can pay the exact amount of this plot. Therefore, what the trick we can use? Okay, the trick we can use, we will try to fit either a square or rectangle so that this area will get enclosed. Therefore, the one way I can do is I can enclose this shape into a rectangle or a square. Now, why these are two geometrical shapes I am using? Because to find out the area of a rectangle or square is known to us. Correct now? Therefore, let us try to fit this geometrical shape into either a square or rectangle, say like this. Okay, now one can find out this area of this rectangle very easily by finding the length and breadth. The area of this rectangle will be length into breadth. But whether the buyer will pay me a money of this area, suppose the man the person whoever is going to purchase this plot, whether he will pay for me for the area of this region?
No,
No. Why he will not pay? Because this
because
area
that area is greater.
yes, this area is bigger. The person will have a loss. Correct, na? He has to pay more money if he want to pay for this pink shaded region, right? Then what the buyer will do? He will try to fit the square or rectangle which is maximum possible in this plot. Correct, na? Suppose he will draw a plot like he will draw a rectangle or a square like this, which is going to be fitted in the given plot. Then he will ask us to give or to sell this with this much of area. But whether we will be ready to pay or we will be ready to sell with this plot?
No.
No, ma'am.
No, again, because this will be a loss to a seller. Then what one has to do? One has to, no problem with this area, na, the orange region. No problem with this orange region, correct, na? Because this is already fitted into the given plot. Now what one will do in order to find out the remaining area, we will try to divide the given remaining area which is not having any exact geometrical shape. We will try to divide it into the smaller parts. Correct now? See like this. Okay. let me use some others color pen. What we will do? We will make some smaller partitions of the given region, okay, into smaller squares and rectangle. And once we divide into smaller squares and rectangle, it will be easier for us to measure the remaining area as well. Correct now? Then what one has to do? See, look at the sketch I have drawn, red color sketch. What one can do? Whatever this red color squares we have drawn, we can find out the areas of those red color plots or squares or rectangles. Then we will try to make the sum. But still there are some sketches which are not having exact square. These points whichever I am plotting here are not still not having the shape as square or rectangle. Correct now? This dotted lines, whatever dotted areas is not having exact square or rectangle shape. Therefore, to find out the areas of this dotted uh, parts is again difficult. Then what one has to do? One has to make still smaller parts of that dotted line. Suppose I select this region. Then one has to make the smaller regions again. Correct now? And again try to find out this. Means what we have tried to find, what we have tried to do, we have tried to make the smaller partitions of the given plot, either square or rectangle, so that we can find out very easily the area or area equal to that corresponding shape. Correct now? Therefore, if this big square I will call S and the area I will call S1, say. This big orange rectangles, whichever I have drawn now, let me call the area of this as S1, okay. Then let me add up these small squares, okay. Correspondingly, let me name those as S1, S2, suppose this is S2, this is S3, this is S4 and so on. Correct now? Therefore, what we have to do? We have to add the areas of all the smaller partitions we have made of the given sketches. But up to how many steps I have to do this process? Okay, up to how many steps I have to do the process? Till I get the areas of these smaller parts. Therefore, if I call N to be the divisions or partitions, or partitions of given plot, then how many N I have to make? How many partitions I have to make in order to reach the exact area of this plot?
SN.
Can anyone answer? SN. But after SN also I have to proceed now. Because if I write SN, it will take some finite value. But here what we are going to do? We are going to make the smaller partitions of the smaller region. Here there is no facility of having a zoom. If it is possible here, we have to make many partitions so that in order to find out the given region. Therefore, we are going to call this process, we have to take up to infinity. Infinitely many times I have to do this process in order to get the exact area. Therefore, this was actually limit n tends to infinity of the sum. Correct now? Therefore, this is called as limit n tends to infinity sum of areas. Sum of the areas of the partition. Okay. And finally, it will be possible for us to get the exact area of this geometrical shape. And that's why this was defined to be integration. Correct now? What is word-to-word meaning of the word integration?
Summation.
Integrate means? Yes, it is summation. मराठीमध्ये आपण त्याला गोळा करणे असं म्हणू शकतो ना. इंटिग्रेट करणे म्हणजे काय? गोळा करणे. आपण काय गोळा केले? We have integrated the areas of these 5 partitions. smaller partitions of this plot, and that's why integration was defined to be the limit of sum of what? Sum of the smaller partition. Correct now? And that's why a new concept was defined as integration. Initially, the concept was defined like this only. Later, it was understood that this concept is inverse of differentiation. Therefore, we have introduced many formulas by knowing this is the inverse of differentiation. Correct now? Any doubt about this? How integration is being defined?
No, ma'am.
Good. Now let me come to the next point. As you have told me already that integration is defined to be the area bounded by the curve. Na? Area bounded by the curve. Now what we will do, we will work out some one or two examples in order to understand this. Okay. Therefore let me write graphically integration of some function, integration of some function gives the area bounded by the curve. Correct na? Area bounded by the curve and x-axis. Why I am saying x-axis? Because the curve we are taking under the consideration is y equal to f of x, and integration we are doing with respect to x. Integration a to b y dx means integration a to b f of x dx. This is what we are following, and that's why this is giving us the a. Suppose this is the curve, okay, and these are my limits a and b. Then what we will do? We will drop the perpendiculars at A and B. Correct? This is my x-axis, this is my y-axis, and this is the curve y equal to f of x. Then integration is giving us the area of this shaded region. That is area bounded by the curve and x-axis. Area bounded by the curve and x-axis. Correct? If you change your function from instead of y equal to f of x, if I write x equal to f of y, and if I differentiate with respect to y, what will happen? Yes?
The region will come on y-axis.
Yes, region will come bounded with y-axis. Correct now? Let me show you here. Suppose this is the same. Now, here is your a and b. Correct now? Because a and b are now the limits of y. Then here we have to drop the perpendicular on y-axis, and this will be the area shaded. But conventionally we are using this symbol right now, y equal to f of x, and integration is taken with respect to x. Let us work out with an example to check exactly whether it gives the area bounded by the curve with x-axis or not. Okay, let me start with a simple example of y is equal to x, and I will take the area as 0 to x. I will take the area as 0 to x. Okay, what is integration 0 to x of a function x dx? Integration is
X square by 2.
x square by 2. If I put the limits of 0 to x, how much is the value? This is x square by 2 minus 0. That is x square by 2. Okay. Now let us check graphically whether it is exactly giving us x square by 2 or not. Okay. Y equal to x is going to represent a straight line bisecting the first quadrant. Correct, na?
Yes, ma'am.
Bisecting the first quadrant. And suppose somewhere here is the value x. Then what is the area bounded by the curve and x-axis? Lower limit is 0, upper limit is some x. Okay. Let me drop this perpendicular. Now this will be the area na? Under the consideration. Let me shade the area. Correct? This is the area. Okay. But what this area is going to represent? This is going to represent a triangle, na? Let me name the coordinates. This is O. Let this be A. This be B. Therefore, this will be actually area of a triangle O, A, and B. How can we find the area of this triangle now? Half base into height. Correct now? What is the value of your
Yes, ma'am.
base length?
X.
Yes, this is x. What is height? Can anyone tell me this height?
Again, it is X.
X.
Yes, because the function we are taking is y equal
Y
to
is equal to X.
good. Therefore, what is the value we have obtained? Half x into x.
X square by 2.
Square by 2. Therefore, with this example, we have checked out that whether the integration is giving us the area or not, and we have found it correct. Okay, let me take one more example. Let me take some y is equal to constant, say a. This is constant. Okay, and again I'll take the limit as suppose 0 to x. 0 to x. Okay, let us find out the calculation. By integration first, between the limits 0 to x, a dx. What is the integration?
0.
0.
Ax, na? Ax between 0 to x. Therefore, if I put upper limit, this is x. If I put lower limit, this is 0. So, for finally, we have the value as ax. Correct? Okay. If you are getting confused with x, you can change it to some other constant b also. Now, let us check by graphically. How can we represent a function y equal to constant on a graph? What it is going to represent?
Horizontal line parallel to X
Good.
axis.
Horizontal line parallel to x axis. And where it is going to cut at y? What is this coordinate?
At A.
Point A.
Good. This is at point A. Somewhere here, let me mark the position x. Therefore, what is the area bounded by this straight line between the region 0 to x? 0 to x. Therefore, let me just put a line here. Therefore, what is the area under the consideration? This much will be the area, na? But what this area is exactly? It's a rectangle, right?
Area of rectangle.
Let me name the coordinates. This is origin A, 0, O, A, B and C. Therefore, let us just check out what is the area of a rectangle O, A, B, C. Yes, this is length into breadth.
Good.
What is the length?
X.
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 What is the breadth?
And breadth
A.
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 A. Therefore, again we are getting this as AX. Correct now? Therefore, again we have verified that integration of a function is giving exactly the area. Let us work out one more example. Y equals to under root a square minus x square for x belonging to minus a to plus a. Minus a to plus a. What will be the curve? Can anyone tell me?
Circle.
Yes, it is a circle because if I make a square on both the sides, this will be y square equal to x a square minus x square. Therefore, it is x square plus y square is equal to a square. Therefore, this is a circle with radius
A.
A.
a and origin at
Ori 0.
0. Center at origin, sorry. Center at origin. Right now? But what is the area bounded by the curve? Is the whole circle will be there? Actually, integration is giving us the area bounded by the curve with x-axis. No? Therefore, this will be a curve and area bounded by this will be this much only. Correct now? This lower region will not appear. This will be a curve, area bounded by the curve with x-axis. Therefore, actually it is giving us the area of a semicircle. Okay, let me do an integration. Integration minus a to a y dx. Correct? So this is minus a to a under root a square minus x square dx. Are you remembering what is the integration of this? Under root a square minus x square? You might have forgotten these formulas during this lockdown. Hmm? So please recall all the formulas. Correct? And this is between the limits minus a to plus a. Right? If I put plus a, this term will be 0. If I put minus a, still this term is 0. Therefore, we have to focus on the first term only. A square by 2 is a constant. If I put the value x is equal to a by 8 is 1, sine inverse 1 is pi by 2. Similarly, if I put the value as minus 1, minus 8, sine inverse of minus 1 will be, sine inverse of minus 1 will be,
minus 5.
minus pi by 2. And minus of minus pi by 2 will be plus
0.
pi. Minus minus 2 pi by 2. It's pi. Correct, na?
Yes, ma'am.
Pi. Therefore, what is the value we have obtained? Pi a square upon 2 is the value of integration. Now, let us find out the area of the semicircle. What is the area of circle?
Pi r square.
Now, for this, radius is a, na? This is pi a square. Correct? Then, what is the area of semicircle?
Pi a square by 2.
Good. Pi a square upon 2. And what we have obtained after the integrations? Pi a square upon 2. Correct, na?
Semicircle of
Correct? Yes, is someone asking me doubt? Is there any doubt on this?
No, ma'am.
Good. Therefore, with the help of examples, we have checked out that how graphically the integration concept is giving us the area bounded by the curve at x-axis. This is what we have already studied. Now, in this topic, we are going to study the approach by Riemann, purely arithmetic approach given by Riemann. Therefore, throughout this topic, throughout this paper, we are not going to use the formulas anywhere. We are going to find out the value of integration by using the Riemann's arithmetic procedure. Okay. Now, to understand Riemann's arithmetic procedure, we have to deal with some basic concept. Okay. Therefore, in order to find out the integration, one important fact is the function should be bounded. Okay, because for not bounded function, it is not possible for us to find out the area bounded by the corresponding curve. Okay, therefore, throughout this unit, throughout this paper, the assumption will be the function should be bounded on the given interval. Then only we will be able to find out the integration of the given region or given curve. Therefore, in order to understand Riemann's method of integration, let us try to understand the definition. The first definition of this topic is partition. First definition is partition. Okay, here I'll write this statement throughout the unit. Throughout the unit, the function will be assumed. This may be the question for your objective, na? Whether we can find out the area of an unbounded function. The function will be assumed to be bounded. Unless otherwise stated. Unless otherwise stated. Okay. And here I equals to closed interval a to b, the closed interval on which we are going to find out the area of the given region. Now let me define partition. Now the word partition itself tells you a meaning. You are going to make the smaller partitions, smaller divisions of the given region. Okay. Therefore here partition is defined to be the finite set P of points of this given interval. Okay, let me write. Partition means a finite set of set P of points say x0, x1, x2 dot dot up to xn, where how we are going to find those points. Okay, first point is x0 less equal by x1 less equal by x2 less equal, and will be continued to xn, where last point is b. Correct? That is a very simple meaning of this partition is, this is my real line and this is the closed interval a to b. Now we are going to make the divisions, smaller partitions, smaller divisions of this closed interval. How can we make the divisions of this interval? By putting some points in between. Na? Therefore, the first point of the interval is called as the first point, say x0, then later it is x2, x1, x2, x3, so on, and this last point was considered to be xn. This last point is considered to be xn. Correct? Okay. Therefore, this set P of points, say x0, x1, x2 till xn is called as partition. Okay, that is, we are going to divide the given closed interval AB into some parts. Here, how many parts, how many points we have taken in all? x0, x1, x2 up to xn. How many points we have?
N plus 1.
Yes, the partition contains how many sub-intervals
1
then?
plus.
Partition contains n plus 1 points, no doubt. Correct, na? Because here from 1 to n, these are n points added with this x0. Therefore, there are in all n plus 1 points. And how many sub-intervals? The partition P contains
N intervals.
n plus 1 points, and this closed interval are n intervals. Good. First sub-interval is x0 to x1. Second sub-interval is x1 to x2. Continue this. The last sub-interval will be, or let me write some ith sub-interval. Some xi minus 1 to xi. Correct, na? Xi minus 1 to xi. And what is my last sub-interval?
Xn minus
1
to xi. Okay, therefore partition is the set of points which satisfies this inequality relation. x0 less equal by x1 less equal by x2 till less equal by xn. Therefore, partition P is the set of these n plus 1 points, and these are the n sub-intervals. Correct, na? These are the n sub-intervals of closed interval AB. These are n sub-intervals of the closed interval AB. Correct? Let us take an example. Suppose we are given with interval 0 to 10, say. Okay. How can we make the partitions of this interval? How many ways are there to make the partitions?
10.
10 ways you are saying, or 10 points you are saying?
10 points, madam.
10 points. Not necessarily, one can make 100 points also, na? One can make 100 points, one can make 500 points. Therefore, there are many ways to make the partitions of the given interval 0 to 10. Rather, I will say infinite ways of partitions. Correct, na? I think you have given the answer 10 by plotting the points as 1, 2, 3. Correct, na? 4. This is what? One of the way of partition. It is not always essential to make the partitions of equal length. One can make the partitions of unequal length also. How can we find out the length of these subintervals? Suppose I want to find out the length of this ith subinterval. Hmm? What is the length of subinterval? 2 to 3?
Mod of
1.
3 minus 2.
1,
One.
right? 3 minus 2. Similarly, what is the length of this ith subinterval?
I minus
Mod of
I
I
plus
minus I minus 1.
I minus 1. Is it true? Or is it xi minus 1?
Xi minus
xi
Xi minus 1.
minus xi
Ah,
minus
good.
1.
Xi minus 1. And we are going to call this with a symbol delta. Delta is going to represent length of, this symbol delta xi is going to represent length of ith subinterval. Correct? Length of ith subinterval. Is there any doubt with the definition partition? We can make the partitions, means we can divide the given interval into number of subintervals. Therefore, if given with an interval, one can make infinite number of partitions. Therefore, the definition of partition is finite set of points P, finite set of points x0, x1 up to xn, where this relation is going to hold. X0 less equal by x1, less equal by x2, less equal by xn. Now one may have a question, instead of less equal, what will happen if we write it as strictly less? Hmm? What will happen, parents? With this strictly less, the problem is, see what the problem is. Here, whatever the subintervals we are making, if I take the union of length of all these subintervals, if I take the union here, this length added with this length, added with this length, added with this length, then this is going to create the length of our original interval. Correct now? But if we write instead of less equal, if it is strictly less, then these middle points will be excluded. Correct now? Okay, because the interval will be now an open interval a to x naught, open interval x naught to x1. Correct? Open interval x1 to x2. Therefore, if I take the union of length of the intervals again, the points will be excluded. Therefore, while doing the partition, one should not be allowed to take strictly less. This inequality will go with less equal. That is, partition will be made by taking the points as x0 less equal by x1, less equal by x2, so on up to less equal by xn. Is this point clear to everyone?
Yes, ma'am.
Okay. Next, we will go to the upper and lower sums. Next definition is upper sum and lower sum. Upper sum and lower sum. Okay, one more. This interval a to b, may I say it is bounded on these subintervals as well? A x0, x1, first subinterval, x1, x2, second subinterval. Therefore, the given function is bounded on these subintervals also. Now, knowing the function is bounded, one can find out the supremum and infimum value of the given function. Okay, therefore, here I will write as f is bounded on closed interval AB, then it is bounded on each subinterval, bounded on each subinterval corresponding to each partition P, corresponding to each partition P. That is for every partition. Whatever is the partition we are going to make, the function will be bounded on the subinterval. Okay. Now let capital Mi be the supremum of F in ith subinterval xi minus 1 to xi, and small mi be infimum of F in xi minus 1 to xi. Okay, we have seen the concept of supremum and infimum in the previous lecture. Supremum is least upper bound, infimum is greatest lower bound. Correct na? Therefore, as the function is bounded, it must have suprema, it must have infima on every subinterval. Here is the symbol we are using. Capital Mi be the supremum of given f in the ith subinterval. Small mi be the infimum of f in the ith subinterval. Therefore, the first sum, upper sum, is defined as the first sum of Riemann integration. Upper sum is defined as, the notation used for the upper sum is capital U into bracket P comma F. Okay. Therefore, this U stands for upper sum with respect to the given partition of a given function. F. This is the symbol we are using, and the definition is, this is summation I equal to 1 to n capital Mi into delta xi. Okay, if I run up the sum over I, what is the value? M1 delta x1, M2 delta, continue up to Mn delta xn, Mn delta xn. Now we will try to understand how this, what this upper sum is going to tell us. Okay, as the function is bounded, time being let me assume the function continuous as well in order to show you how this upper sum is going to work out. Okay, therefore let me assume this is my function here. Time being one may assume continuous. It is bounded no doubt. Correct na? But I have plotted this on the 2D plane, x and y axis. Somewhere here be the interval a to b. Okay, so we will just join these points with the curve. Therefore, according to our integration definition, this much area is under the consideration, right now? This much area is under the consideration. Is under three partitions of the given interval. Okay, let me assume this is my first point x0. Let this be x1, let this be x2, and let this be x3 for showing you. Therefore, how many points I have used? 4 points for the partition I have used. Therefore, in all it will generate with 3 subintervals. Okay. Now, what this m1 is going to tell us? M1 will be the supremum value of the given function in first subinterval. M2 is supremum value in the second subinterval. And here we have only 3. Na? Therefore, let us just draw the subinterval points, or let us join these subinterval points with the given curve. Right now, I have just joined it. Now let us try to find out where is the location of M1. This is the first subinterval, right? This is the first subinterval, and this is my value of delta x1, no? Correct, no? This is delta x1. Okay? This length of the first subinterval. What is delta x2? Length of second subinterval. And delta x3 will be length of third subinterval. Therefore, respectively, this is delta x1, this is delta x2, and this is delta x3. Now we will try to find out what m1 delta xn is. Can anyone tell me what is the supremum value of the function in this interval? Where is the curve starts? Can anyone tell me what is the supremum value of the function in this subinterval? This is the curve under the consideration. This much is the curve. What What is the supremum value? Let me just mark this. This is M1, na? Okay. What is the supremum value in the second subinterval? Somewhere here. M2 I will call, and this is the supremum value in the third. Right? So these are the respective positions of M1, M2, M3 I have shown. Correct. Now what is M1 delta X1 is going to represent? If you just look at this, you can assume this as the breadth, you can assume this as the length. Therefore, length into breadth, this will give, the first term will give us the area of a rectangle with breadth delta x1, breadth delta x1. No? This is breadth and this is length. This is the breadth delta x1, this is the length m1. Therefore, what it is going to represent? Let me complete the rectangle. I'll just take another pen. Therefore, this will be a rectangle under the consideration with length m1 and breadth delta x1. Therefore, this is giving us the area of the first rectangle. Just check. This is the area of this rectangle. Correct now? Okay. Similarly, let me go for finding the value of M2x2. M2x2 is again giving us the area of the rectangle with breadth delta x2 and height m2. Means this one will be my area under the consideration. Let me just shade the region. Okay. This is the area of second rectangle. What about M3 delta x3? M3 delta x3 will give us the area of this rectangle. Let me just shade the region. Correct? Understood this geometrical sketch? M1 delta x1 length of this rectangle. M2 delta x2 length of this rectangle. M3 delta x3 will be the length of this rectangle. And if I sum up all these all these areas, this total area will be slightly above the actual area bounded by the curve, and that's why the name of this sum is upper sum. This is somewhat bigger, somewhat greater than the actual area bounded by the curve. I hope there is no difficulty along with this definition, right? Now let me just tell you what is lower sum. Second definition. The second definition was denoted with capital L with respect to partition for the function here, and the definition is summation I equal to 1 to n small mi delta xi. If I run up the sum, this is m1 delta x1, m2 delta x2, and so on up to mn delta xn. Okay, let me show you the sketch very similar to the upper sum. Don't mind, these straight lines are not going straight actually. Okay. So this is the curve, right? Now let me draw this as A and B. This is f of x. Again, I'll just put 2 points only. This is A equal to x0 is the first point. Here it is x1, x2 and x3. Therefore, again we have found 3 subintervals. Let me join the subintervals with the curve, points with the curves. Okay. Now have a look. This is m1 delta x1. Now m1 is the infima. Now can anyone just check where is the infima of the function here in the first subinterval, in this first subinterval? According to the sketch, may I say this is the infima? Small m1. In this second subinterval, this is the infimum value, say m2. And according to the third, this will be the infimum value, say m3. Right? Now, what is m1 delta of x1? Small m1 delta x1. Small m1 delta x1 is again the area of the rectangle with length m1 and breadth delta x1. Let me draw this. Where is m1? Here is m1, no? And this is m1 into delta x1. Therefore, this is the region. First region m1 delta x1. What is the second region m2 delta x2? This is the region m2. This is the level. Therefore, this is the area m2 delta x2, right? And what is the third m3 delta x3? Here is the position m3. Therefore, this is the shaded region. Therefore, here if I make the addition of all the three sums, it will give us the area slightly below the actual curve or slightly lower to the actual curve. That's why the name is lower sum. That's why the name of the sum is lower sum. Okay. Any doubt up to this? Both the sums are defined by the mathematician Darboux. Therefore, those are also called as Darboux upper and lower sums. Darboux upper and lower sums. Okay. Any difficulty about the sums? This is upper sum. This is lower sum. Okay. I just want to show you with the animation. Is the screen visible to everyone? Check. This is the upper sum and lower sum calculated. I have not shown you below x-axis also, but if I take you to below x-axis, this will be the upper and lower sum. This is upper sum, this is lower sum. This is upper sum, this is lower sum. Due to a drastic change in the curve, we are observing this. Okay. So this is what an animation is. Okay. Understood both the definitions? Upper sum and lower sum?
Yes, ma'am. Yes, ma'am.
Okay, good. If you understand the geometrical aspect of both the summations, then it is very easy for you to understand the Riemann of integrability, or with the help of these two sums, how one can find out the actual integration of the given curve. I will take a present. Wait. Thank you for watching today's lecture.